Ever wondered why time seems to fly when you're having fun but drags when you're bored? Could it be possible that time changes depending on your perspective? A peculiar notion, isn't it? Today we're diving into a topic that has intrigued minds for over a century: Einstein's theory of relativity. We'll explore how this revolutionary theory challenges our understanding of time and space, hinting at a connection between our perception and the fabric of the universe. Let's embark on this journey to unravel the mysteries of the universe through Einstein's theory of relativity. Before Einstein, Newton's laws of motion were the cornerstone of our understanding of the universe. Newton's laws painted a picture of a predictable, clockwork universe where space was absolute and time flowed uniformly. But as we delved deeper into the cosmos, some inconsistencies began to surface, and it was Albert Einstein who rose to the challenge with his theory of relativity. Einstein's theory of relativity is built on two fundamental ideas, or postulates. First, the laws of physics are the same for all observers, regardless of their state of motion or where they are in the universe. That means whether you're standing still on Earth or zooming past a planet in a spaceship, the laws of physics don't change, they're universal. The second postulate is that the speed of light in a vacuum is constant and is the same for all observers, no matter their state of motion or of the source of light. This means that light will always travel at the same speed, about 300,000 kilometers per second, regardless of how fast you're moving when you measure it. These two postulates challenge the very core of Newton's laws. For instance, according to Newton, if you're standing on a platform and a train passes by at 60 kilometers per hour, and someone inside the train throws a ball forward at 20 kilometers per hour, you'd see the ball moving at 80 kilometers per hour. But Einstein's theory throws a curveball. If instead of a ball it's a beam of light, you wouldn't see the light beam going faster than light speed, despite the train's speed. It would still appear to move at the speed of light. This defies our everyday experiences and was a revolutionary idea. So Einstein came along and changed our perspective, but how exactly does his theory work? Well, that's a question that leads us deeper into the fascinating realm of relativity, a journey that will continue in the next segment. Now imagine you're traveling at the speed of light. What happens then? This thought experiment takes us to the heart of Albert Einstein's special theory of relativity. You've probably heard the phrase, "time flies when you're having fun." But according to Einstein, time actually does slow down when you're moving fast. This is a concept known as time dilation. The faster you move, the slower time passes for you compared to someone who is stationary. This might sound like science fiction, but it's a scientifically proven fact. GPS satellites, for instance, have to account for this effect because they're moving much faster than we are on Earth. Now, let's talk about length contraction. This idea is just as mind-bending as time dilation. According to Einstein, as an object moves faster, it gets shorter in the direction of motion. So if you're looking at a spaceship zooming past you at near the speed of light, it would appear shorter than if it were standing still. Sounds impossible, right? But this is what the math of special relativity tells us. A cornerstone of special relativity is the constancy of the speed of light. No matter how fast you're moving towards or away from a light source, the speed at which light reaches you remains the same. This speed is a staggering 671 million miles per hour and is the same for all observers, regardless of their state of motion. These ideas challenge our everyday experiences. They tell us that the universe doesn't adhere to our intuitive sense of how things should work. Instead, the universe follows its own set of rules that Einstein decoded to give us a deeper understanding of the cosmos. So time and space are not absolute, but relative to the observer. But what about gravity? Let's delve into that in the next segment as we explore the general theory of relativity. The journey is about to get even more fascinating. How does an apple falling from a tree relate to the moon orbiting the Earth? This is where the general theory of relativity comes into play, a theory that Einstein himself described as his happiest thought. Let's delve into this. The general theory of relativity, unlike the special theory of relativity, includes the concept of gravity. Here's the most interesting part. It describes gravity not as a force, but as the curvature of space-time caused by mass and energy. It's a little like a bowling ball on a trampoline. Imagine space-time as a trampoline, a flat, stretched-out surface. Now place a heavy bowling ball in the center of the trampoline. The bowling ball, representing a massive object like a star or a planet, causes the trampoline to curve or dip around it. This is what mass does to space-time. It warps it, bends it, distorts it. Now, think about a marble rolling around the edge of this dip. It doesn't go straight, but instead starts spiraling inward towards the bowling ball. This is similar to how planets orbit around the sun. They are simply following the curves in space-time created by the sun's mass. So, when an apple falls from a tree, it's not that some mysterious force is pulling it down. Rather, the apple is following the curvature of space-time created by the Earth's mass. It's the same with the moon orbiting the Earth. The moon isn't being pulled by the Earth as much as it is following the curve in space-time that the Earth creates. The general theory of relativity is not just about gravity, though. It also predicts the existence of black holes and gravitational waves, phenomena that have been confirmed by observations in recent years. Black holes, regions of space where gravity is so strong that nothing, not even light, can escape, are extreme examples of space-time curvature. They are like the bowling ball that has made such a deep dip in the trampoline that the marble cannot escape it. Gravitational waves, on the other hand, are ripples in space-time caused by the acceleration of massive objects. They are like the ripples created when you toss a stone into a pond. In 2015, a century after Einstein proposed their existence, gravitational waves were finally detected, proving yet another prediction of the general theory of relativity. To sum it up, the general theory of relativity paints a picture of a universe where space and time are intertwined, where mass and energy warp this space-time fabric, creating what we perceive as gravity. It's a universe where massive objects can create ripples in this fabric that we can detect billions of light years away. The universe is indeed a fascinating place where massive objects bend space-time and create what we know as gravity. So, how does this theory affect our daily lives? Well, the theory of relativity, both special and general, has far-reaching implications and applications that we encounter in our everyday lives. Take global positioning system technology, or GPS for instance. It relies heavily on relativity. GPS satellites are moving relative to the Earth and are further from its gravitational pull. Consequently, time ticks faster for them compared to devices on Earth due to both special and general relativity. To correct this time discrepancy and ensure accurate positioning, GPS systems account for these relativistic effects. Then there are black holes, fascinating phenomena that are a direct prediction of Einstein's general theory of relativity. These are regions in space where gravity is so strong that nothing, not even light, can escape. The study of black holes has led to breakthroughs in our understanding of the universe and the laws of physics. Lastly, the theory of relativity has also given us the concept of an expanding universe. In fact, it was Einstein's equations that first suggested the universe could be expanding, a theory that was later confirmed by observational evidence. So, while the theory of relativity might seem daunting and abstract, its implications are quite tangible. From the technology we use to our understanding of the universe, relativity is deeply woven into the fabric of our existence. Einstein's theory of relativity, though complex, has profound implications that reach into our daily lives. So we've journeyed from Newton to Einstein, from the absolute to the relative. We started with the basics of the theory of relativity, which challenged our conventional understanding of space and time. We then delved into the special theory of relativity, which asserts that the laws of physics are the same for all observers, regardless of their motion or lack of it. From there, we ventured into the general theory of relativity, where we learned about the curvature of space-time around massive objects, and how gravity is not a force but a consequence of this curvature. Finally, we explored the implications and applications of these theories, which have shaped our understanding of the cosmos and have found their way into everyday technologies like GPS. The journey was complex, yet fascinating, and we hope it has inspired you to delve deeper into the mysteries of our universe. Next time when you feel time is flying or dragging, remember it's all relative.